Hello, my name is Corey Beasley, and I'm a part of Challenge 2016. And today I'm going to show you how to find the area of a torus, or a donut, essentially. It's just another name for it. This shape right here. So, the first step is, number one, we have to understand that this is a three-dimensional shape, meaning that there are going to be three planes involved in finding the area, or there are going to be multiple steps as opposed to just integrating or just using an equation. So that's the first thing to consider. So I'm going to go ahead and start by drawing the shape, which I just did, on the XY plane, like this. So our first order of action is we're going to actually try to find a cross section of the donut, or we're going to take a circle out of the donut just like this. Now, before we go ahead and do that, I'm going to explain the initial rules of the problem, or what we are given, the boundaries. So we're given an XY plane, and we are told to find the area of a torus with a radius of r, and it is capital R. That's the distance that's away from the origin, and it's actually rotated around the y-axis. Oops, sorry. We have to find the area of that. Let me go ahead and label the axis. So that's the initial problem that we're given with. So, step one in this problem is we're going to have to go ahead and take a cross section of the donut, a circle. So if we go ahead and take this circle out of the donut, we can go ahead and make it bigger right here. And we're going to work with this first. So imagine that this is the x-axis going across the donut. We're going to go ahead and try to find a secant that goes across the donut at another point that isn't the x-axis or the diameter. So I'm going to go ahead and draw this. Now, we want to find the length of this secant. We don't have actual values, but we're actually going to use arbitrary values, such as an a. So we're going to go ahead and divide the secant in half like this. And we're going to assign this part of this secant right here an a value. Now that we have the a value, we're going to go ahead and extend the radius, because remember the radius all over the circle is the same size. Notate that as r. And this right here, this stretch, we're going to notate as z. Now we're going to use Pythagorean's theorem to find the value of a. A is the secant, or it's actually half the secant. So I'm going to go ahead and work that up here. We're going to have a squared plus z squared. It's going to be equal to r squared. Now at this point, what our objective to do is we're going to go ahead and try to isolate a, get a by itself. So a little bit of algebra, and we can figure out that a is going to be equal to the square root of r squared minus z squared. So now that we have this, we can move on to the next step in the problem. Now, if we were to try to find the area of, or let's say actually that we were going to look at the torus from another view now. We've been looking at it from the view that the planes are x and y. However, we're going to change that up. As we know, in a three-dimensional plane, we have, as the name suggests, three dimensions. We have the z dimension right here, x right here, and the y right here. Previously, we were looking at the torus from the xy perspective. However, we're going to now go to the xz perspective. And this essentially means that we are just looking at the figure from the overhead view, or the top view. The y-axis is now no longer visible. So this is what it looks like from this view. Now at this point, what we're trying to do is find the area of the torus from this view. So I'm going to go ahead and erase, give us a little bit of room. Now if we increase the size of the figure, we're going to have the torus looking like this, with this being the origin. We have the x-axis and the z-axis. This is the outer parameter of the torus. And we're going to go ahead and analyze the values that we are given. So we know that this across here, I'll actually draw on this side. This across here is equal to 2a. We know that the distance that the torus is from the center of the circle is equal to capital R. And we know the radius, well actually we're not going to be using the radius. We're going to go ahead and be using the double a value that we found. I'm going to go ahead and write a back up here is equal to the square root of r squared minus z squared. Now, at this point, we're trying to find the area basically of the whole torus from the overhead view. It's going to look like this essentially. In order to find the area, we're going to go ahead and use the formula to find the area for a circle, which is the area of circle is equal to pi r squared. Now, if we were to elaborate a bit on this formula, we can go ahead and figure out if we were to find the area of a donut-shaped circle or a ring, we're going to take the area of the larger ring and then subtract the area of the smaller ring. So let me go ahead and erase this so we have a little bit more room to work with. So that's going to give you pi, which is distributive, so we're going to go ahead and put that on the outside. Pi is equal to the area of the larger circle. Now remember, the radius of the larger circle is going to be this r value plus the a value, because the a value extends from one side of the circle to the other, and that's equal to 2a. So this value right here is equal to a alone. So it's going to actually be r plus a, which is going to be the radius of the larger circle, squared, minus r subtracted by a, the radius of the smaller circle, squared. We go ahead and we simplify this, and we get the area of the circle is going to be equal to, let me just see right here, it's going to be actually equal to 4 times pi times r times little a. And we can refer back to this formula we found with the Pythagorean theorem. And to give a value to a, we can see that a is going to be equal to the square root of r squared minus z squared. So we got the area is essentially equal to 4 pi r square root of r squared minus z squared. Now, at this point, we're going to go ahead and start comparing the torus, or the overhead view of the torus, to a standard rectangle. And that's going to give us a little bit more insight on how to solve the problem. So I'm going to go ahead and draw the overhead view of the torus. And I'm actually going to draw a rectangle beside it. And I'm going to segment the torus in a similar way to the rectangle, so that we can have a little bit better of a perspective. And we can understand that the rectangle's area can be equal to the torus's area. So as we remember before, we found the area of the torus to be equal to 4 pi r a. So we're going to now imply this area on the rectangle. So as we know, the diameter of the torus is equal to 2a, which we calculated earlier. So I'm going to make this the length of the rectangle, or the width, sorry, equal to 2a. And now the length of the rectangle is actually going to be found by finding the the circumference of the center of the torus. Now the circumference of the center of the torus can be basically found by the circumference formula, pi times the diameter, pi d equals circumference. If we were to imply this formula on the torus, we would get we know that the radius is equal to r, and then we get another r on this side, so it's actually not going to be 2r. So this value right here is going to be pi d, or basically 2r times pi, because 2r is equal to d if you're looking at the torus from overhead. So now, if we go ahead and multiply 2 pi r times 2a, we're actually going to get 4 r pi a. Now we'll notice that this formula is the exact same formula as we had for the area of the torus from overhead. And this is where we actually make a connection between the two, because not only do the figures look the same and are segmented the same, but they now have the same formula for the area, which is the golden formula of 4 pi r a. Now, as we were able to compare the torus to a rectangle, or the cross section of a torus to a rectangle, we can do the same as far as comparing the torus itself, the actual donut, to a cylinder. It's basically the same thing. We found the area for each, and we can now compare the two. So, if we were to find the area of the cylinder based off of the formula for the area of the rectangle of the cylinder, we will multiply the circle on the cylinder by the area. And the circle of the cylinder is actually going to be equal to pi r squared, the standard formula for a circle. Pi r squared. like that. And we're going to go ahead and multiply that by, sorry, one second, let me make sure I have my math correct here. So yes, the volume of the cylinder is going to be equal to, and let me go ahead and write this a little bit more clearly. It's going to be equal to 2 pi r times pi r squared, or times 2 pi r squared actually. Go ahead and multiply those together, and we're going to get, actually let me check my math really quickly, make sure that everything is going smoothly. Okay, so yes, we saw the length of the rectangle based on the last diagram is actually equal to 2, sorry for the pause, it's actually equal to 2 pi r. And again, the area of a circle of any sort is equal to pi r squared. Now, if we were to find the area of a cylinder, we just simply multiply the area of the circle by the area of the rectangle. I mean, the area of the length, or the length of the rectangle, sorry. So that's actually going to be 2 pi capital R times pi r squared, and that's going to give us 2 capital R pi squared r squared. I'm going to write this a little bit more clearly. 2 capital R pi squared lowercase r squared equal to the area of the cylinder. Now, the rest of this is conceptual. As you remember, the rectangle used to form the cylinder is actually the same as a cross-section of the torus. And we now can understand that if you make each of these three-dimensional, or you create a cylinder out of this and a donut out of the torus cross-section, they're actually the same figures, just shaped in a different way. So the area of the cylinder is actually equivalent to the area of the torus. And that's how we can find that 2 capital R times pi squared times r squared is equal to the area of the torus. Now, to complete the formula finally, we're going to do one last substitution. And that is going to be that r squared is going to be equal to z squared plus, or actually I'll just go ahead and say r is equal to the square root of z squared plus a squared. Because we're asked to find the volume, we can't use one of the things we were given, the radius. So that's now going to be that 2 capital R pi squared times r squared, which it can be substituted for z squared plus a squared. Squared. This square and the square root cancel out. And this is the final formula for the area of a torus. So to sum it up, we basically found the area of a cylinder, and we showed that the rectangle used to form the cylinder is equal to the cross-section of the torus, and we multiplied both by the area of the circle, and we're able to get the final formula. Again, my name is Corey Beasley, and thank you for watching the video.